Good afternoon all. Today in this particular session we will see double integration, and as per our curriculum we have to see two methods for double integration. One is trapezoidal rule and second one is Simpson's rule. In previous lectures we already discussed how to use trapezoidal rule and Simpson's 1/3 and 3/8 rule to solve the problems related to integration. So during the previous sessions we discussed that we consider a plane. For example, we want to calculate the area of a surface or any object, but that was a 1D problem. Now in case of double integration we will be focusing on 2D problems. For example, consider a rectangular shaft. So the cross section of the shaft will be a rectangle, and for that particular cross section if we take integration then we can calculate the area of that rectangle. But if we take the integration along the length of that shaft, then that will be a second dimension, and through that integration we can calculate the volume of the shaft. So this is the basic approach that we use for double integration. So in simple words, what I would say, when we go for single integration we calculate area or dimension, area of a 1D component, I would say. And when we say double integration, then we talk about the second dimension, for example, volume in case of a shaft. So let's start with the trapezoidal rule. The basics and the fundamentals of double integration is similar to the previous methods that we already discussed. But when you look at the formulae as we go ahead, then you may realize that to memorize these formulas are challenging. So we need to understand how we derive those formulae and how we can memorize. So double integral is evaluated numerically by two successive integrations in x and y direction, considering one variable at a time. So in this particular problem, there will be two variables. For example, in case of rectangular shaft, so cross section area will have one variable and the length of that shaft will have second variable. So when we are calculating the area of that rectangular shaft, we will assume length as a constant. And when we calculate length of the shaft, we assume that diameter or cross section is a constant variable. So this is how we need to proceed. So let's consider this particular equation. I is equal to integration c to d integration a to b f of xy dx dy. So in this particular problem, so the integration a to b f of xy dx is the first part that you need to solve. For example, if you want to calculate the volume of the shaft, rectangular shaft, then this particular integration, this highlighted part will be first you need to do to calculate the cross section area. Once you do that, then we go for the second part of the integration where we will calculate the length of the shaft. So step by step we need to solve this problem. First of all, the inner part we need to solve, and whatever solution we get, for that again we need to take the integration from c to d, and when you do that you will get the final solution for the given problem. Okay, so how to solve this problem? So the basic approach that we use for trapezoidal rule is same. For example, in this case, when we consider the interval a to b, so this interval you need to divide into n equal sub-intervals. Just we discussed in previous trapezoidal rule, and each having a length h. So we need to divide this interval AB into n subintervals and having constant length h. Similarly, for second integration, the interval is C to D. And again that C to D we need to divide into m equal subintervals and each having length k. So the width for interval AB and width for interval CD, so they may be same or different. That depends on you how you solve the problem. So when we decided to divide the interval AB into h parts, so the first value will be x naught, which is equal to a, and last value will be xn, which is equal to b. And between x naught and xn we need to find out the intermediate values. So for that we use this formula, xi is equal to x naught plus ih, where h is the interval, length, or we can say width, and I is the corresponding intermediate value. Similarly, as we discussed, the interval CD is divided into m number of subintervals. So the starting value will be y naught, which is equal to c, and the last value will be yn, which is equal to d. And in order to calculate the intermediate values, we use this formula, yi is equal to y naught plus jk, where k is the length k for interval CD and j corresponding to the intermediate point. So this is how you can calculate all the intermediate points, or intermediate points basically. But one important thing is that if we consider rectangle as a cross-sectional area, then this particular part will be related to diameter of that shaft, and the second part, now I'm highlighting here, that will be corresponding to the length of that shaft. So this is how you need to understand. Now, so far, first integral, that is integration a to b f of xy dx, for that you need to take the integration. When you take the integration, you will get this particular equation. So you can see this particular equation, f of x naught y plus f of xn y plus 2 into all remaining terms, that is f of x1 y plus f of x2 y up to f of xn minus 1 y. So basically first term plus last term plus 2 into all remaining terms. So this is the answer that you get when you take the first integration. And you can compare whatever solution, first integration that you took, with the formula of trapezoidal rule that we derived in previous lectures, and analogically you can compare those. So first term was y naught, so similarly you can see here f of x naught y. Second term was yn, so f of x and y, that is sum of first term plus last term plus 2 into, so 2 is there as it is, into bracket y1 y2 y3 up to yn minus 1. So excluding y0 and yn, all remaining terms you will see in the bracket. So y1 is analogically with f of x1y, y2 is corresponding to f of x2y, and last term will be f of xn minus 1y. So analogically you understood that we are applying trapezoidal rule to inner part of the integration problem, and we are getting this particular equation. And as I mentioned that when we take the first integration, by using one variable, then you need to keep second variable as constant. For example, here you can see x naught first term, xn last term, and x1, x2, xn minus 1, these are the remaining terms. But at the same time, we are keeping the value of y constant. So everywhere you will see y only, because we are keeping that as a constant. Now, in second part, what you need to do? You need to take the integration of this newly derived equation. Let's say equation number 2. And when you take integration of equation number 2 in second part and simplify that equation, you will get this big complex equation. Now you may say that this is very difficult equation to memorize. So what you need to do? You need to take the integration of equation number 2 and try to simplify. You will get this particular form. Okay, now how to memorize this equation? So that trick I will give you, and in that equation I have provided different colors. So these colors will help you to understand the same. Okay, so before I proceed, just a minute, some background noise is there, so I will check it is from which class. Okay, so it is coming from TC division. Okay, so I removed that student from the meeting. Okay. Okay, so again we will move ahead. Okay, so what we did, first of all, we decided the intervals for x and y. Then we took the integration of inner part. And when you do that, you get simplified equation. Again, you need to take the integration for c to d. And when you do that, you will get this equation. Now, when you look at the different parts of this equation, which are highlighted by 3 colors, then you can correlate this with the trapezoidal equation. How? I will tell you. So this equation I is equal to hk upon 4. So in this hk by 4, the first part is h by 2 and second part is k by 2, where h is related to the first integration and k is related to second integration. So h by 2 into k by 2 becomes hk by 4. So that part is understandable. Now when we enter into the bracket, then you will see the part of the equation highlighted by blue color. So there you can see f00, f0m plus 2 into f01, f02 up to f0 m minus 1. So this particular part is the y naught. We can analogically correlate. The second part that you can see, which is highlighted by red color, that you can correlate with the yn, because here you can see this is the first part and yn is the last part, that you can easily understand. Similarly, the third part of this equation, you can see 2 into summation I equal to 1 to n into bracket. There are so many terms. This part we can correlate with the third part of the equation. So first part plus last part plus 2 into all the remaining terms. So this is how you can analogically correlate with this complex equation with the traditional trapezoidal rule. Again, in each segment of the equation, let's start with the first segment. So here you can see F00 is the first part. We can compare with y naught. F0m, which can be correlate with yn, and the 2 into the bracketed term that can be correlated with the last part of the traditional equation. And here you can see we are keeping the value of x as constant and we are varying the value of y. So initial value of y will be 0, then m, then 1, 2 up to m minus 1. So this is how I am trying to tell you how we can correlate this equation that we derived for second integration or double integration with the equation that we derived for single integration. And this is how you logically understand this equation and try to develop the required equation for a given problem. Now let's take one example. Using trapezoidal rule, evaluate I is equal to integration 1 to 2, again integration 1 to 2 dx dy upon x plus xy, taking 4 subintervals. So for both x and y, the number of subintervals are 4, must be 4. And when you look at the upper and lower limits of the integration, so they are same for first and second integration, that is 1 to 2. So for given problem, your function will be f of xy, which is equal to 1 upon xy, let's say equation number 1. And as we need to divide into 4 subintervals in both integrations, so h will be equal to k, which is equal to 0.25. Then m will become equal to n, that is 4. Then when we do that, then for this given problem, and by using the equation that we derived in previous slide, that is here you can see. Just a minute. Just a minute, students, wait. System is very slow here, I can see. Okay, so we derived this equation, and by using this equation, we are developing the equation. Here you can see I is equal to for arc s. So total number of terms are 4. You can see m equal to n equal to 4. So you can see here the first part, so first term plus last term plus 2 into remaining terms, and here the value of x is constant, that is we are keeping one variable constant and we are varying the second variable, that you can see that will be the first part of this equation. Similarly, in second part, we are just taking the value of x from 1 to 2 and we are varying the values of y. So lower term where y is 1, the last value when y is 2 plus 2 into the remaining values of y plus 2 into, now we are taking the value of x as 1.25 constant and we are varying the values of y. So first value, last value and 2 into remaining values. So this is the third part. Now we are keeping the value of x constant to 1.5, and again we are varying the values of y, that is 1, 2, that is first value plus last value plus 2 into remaining values of y, that you can see here, plus now we are keeping the value of x to constant as 1.75, and you are just varying the values of y. So first value, last value plus 2 into the remaining values of y. So this is how you can prepare the required equation for a given problem. Now what you need to do, you need to find out all these terms, f11, f12, f1.1, 1.2 and so on. So you can see it is a tedious task to do it. So how you will do it? So you will put x is equal to 1, y equal to 1 in equation number 1 to get f11. So that you can see here, f11 is equal to 1 upon xy. So x is 1, y is 1, and when you simplify it, you will get f11. Let's take another case where you may be interested to calculate f12. So here x is 1, y is 2. So in equation number 1, you will put x is equal to 1 and y equal to 2. And upon simplification, you will get f of 12 as 0.5. So just put in this equation. So similarly, in this way, you can calculate the value of f for all remaining combinations of x and y, and put all these values in this equation and simplify. Upon simplification, you will get solution as I equal to 0.3407. So this is how we solve the problem of double integration by using trapezoidal rule. Now we will move ahead to Simpson's 1/3 rule. So the approach again is very similar to the trapezoidal rule. So here you can see one integration equation is there, where, as I mentioned, if we consider a rectangular box, then the inner integration, internal part, so that will be related to calculation of cross section area. So you can see I circled a part, integration a to b f of xy dx. So when you take this integration, in case of rectangular box, means you are calculating the cross section area of this box. Once you do it, there will be a second integration from c to d, and when you take that, so you are taking the integration along the length of the shaft, and this is how you can calculate the first of all area in first integration, and in second integration you will be calculating the volume. So this is the basic approach that we discussed previously as well. Now there is a slight difference between Simpson's rule and trapezoidal, that we divide interval AB into 2n equal subintervals for each value of h, each of length h. So in trapezoidal there was n, here it is 2n. Similarly, the interval CD is divided into 2m equal subintervals, each of length k. So previously it was m in case of trapezoidal rule, in case of Simpson's it is 2m. So that is the slight difference. Then we need to apply Simpson's rule that we discussed previously, and when you do it for a particular segment, so for understanding purpose I am taking in y j minus 1 to y j plus 1 integration x I minus 1 to x I plus 1 f of xy dx dy. So first of all we will take the integration of this inner part. When you do it, you will get this equation. So here you can see y is constant that we maintain, and we varied the value of x. So first value of x, xi minus 1 plus 4 into last value of x, sorry, it's not last value, it will be a even value, and f xi plus 1, that is odd value. So this is how we can understand this particular expression, and that is analogical with the Simpson's 1/3 rule. Then in second part, what we do, we take second integration and simplify the same. So again, just like trapezoidal rule, you can analogically correlate. So in first integration, this was the first part. In after taking second integration, this will be the first part. Plus 4 into f of xi y. So similarly, you can see here the second part after taking the double integration. And similarly, f of xi plus 1 y, and after double integration you will see the third part. And again in each part you can see we are keeping x as constant and we are varying the value of j, that is y. Similarly we did for second part as well as third part. So at overall level you can correlate with Simpson's rule, and at individual part level also you can correlate with the Simpson's rule. And outside bracket you can see here it was h by 3, now you can see here h k by 9, where it is nothing but h by 3 multiplied by k by 3. So therefore answer will become h k by 9. So this is how we derive the equation. Now this is how you can derive the equation for each and every interval, and you can calculate the value of integration. Because here what we did, we took a particular interval and we derived this equation that you can see here. So similarly you need to take the prepare the equation for all remaining intervals and add it, go on adding. Let's take one example. Apply Simpson's rule to evaluate integral I is equal to integration 2 to 2.6 integration 4 to 4.4 dx dy upon x plus y. So here the upper and lower limits for both the integration are different, so corresponding value we have to take, and similarly the function f of xy. So the function f of xy will be 1 upon xy. So we will call it as a equation number 1. And for first integration we will take h is equal to 0.2, and for second integration we will take k is equal to 0.3, so that in 2 steps we can solve this particular problem. So that m is equal to n is equal to 2. So how to take the value of h, k and m? So this is very critical question in this particular problem or similar problem. So you need to select the value of h as well as k in such a way that your calculation will be minimized. So here you can see when you take h is equal to 2, your x0 will become 4, So when you put x naught equal to 4, calculations will be easier. Your x1 will be 4.2. So again, calculation point of it is easier. And finally, x2 will be 4.4. So there are only three values of x0, x1 and x2. And calculation point of view also they are easier. And similarly in second integration, when we take k equal to 0.3, the first value of y0 will be 2. The value of y1 will be 2.3 and y2 will be 2.6. So when you look at the values of y, that is 2, 2.3 and 2.6, it is easier to do the calculations as well. And you may ask how we calculate x0, x1, x2, y0, y1, y2. The formula we already discussed. The lower limit will be the value of x0, that is first value of x. The upper limit will be the final value of x, that is x2, and you can calculate the intermediate value, that is x0 plus h. When you do it, you will get 4.2. And if there is any other intermediate point, you can also use formula x0 plus 2h. So x0 is 2 and 2h will be 2 into 0.2. So it will be 4.4. So similarly, you can calculate the values of y as well. So y0 is 2, y1 is nothing but y0 plus k, where y0 is 2, k is 0.3, so the answer is 2.3. Similarly, y2 means y0 plus 2k, where y0 is 2 and 2k, you can see 2 into 0.3 and you will get 2.6 as an answer. Now we calculated all the values of x and y. We have the values of h and k. Now we will prepare the equations. So after taking double integration, you will get this simplified version. And even if you didn't take the integration, you can logically prepare this equation. Here I is equal to hk upon 9. So h by 3 into k by 3 is nothing but hk upon 9, which is equal to f of 4.2 plus 4 into f of 4 2.3 plus f of 4 2.6. So this is first part where you can see the value of x is constant and we are varying the values of y. Similarly 4 into, now we are taking the next value of x, that is 4.2, and which is constant for this particular part of the equation. And again we are changing the values of y. First value is 2, second value is 2.3 and third value is 2.6. Plus third part of equation where we take the value of x as 4.4, which is constant throughout, and we are varying the values of y. So 2, 2.3 and 2.6. So keep one variable constant, vary remaining other variable. So every time you do it, you will get first, second and third equation. So keep one constant, vary other. Change value of first variable, keep it constant, change another values of y. So this is how you prepare it. Then every time, as I mentioned, if we want to calculate f42, then put x is equal to 4 and y equal to 2 in equation number 1. So when you do that, you will get value of f42. Similarly, when you want to calculate f of 4 2.3, put x is equal to 4 in equation number 1 and y equal to 2.3 in equation number 1. You can calculate this part. Similarly, put these values in equation number 1 and you will get the answer. So you can do it, and when you do it, again you need to simplify the equation. H is 0.2, K is 0.3 upon 9. The first part of the equation we got as 0.6559. The second part we calculated as 4 into 0.6246, and third part we simplified as 0.5962, and upon further simplification you will get the value of integration as 0.025. So this is how you can apply Simpson's rule to solve the problem related to double integration. So that's it from my side. If you have any question, the session is open for discussion. Yes, I welcome your question, because particular